Alright, so I'm going to explain how to get the displacement versus position data at a given time step for a spring mass chain. Now, first of all, let's open the ODB file and have it in front of us for obvious reasons. Now, well, this is a spring mass system, right? Now, first off, go ahead and create the XY data, unique nodal displacement, active steps and frames. Um, I have selected a lot of steps here, so I'm just gonna go ahead and select a frame at t equal to 1 second. I can take any second for that matter, but I know that at 1 second the wave has passed through the first few masses. So yeah, at t equal to 1 second, apply, update selection, one frame selected. Okay, now go to node sets, select 1 to M1 200. I'm selecting all of the mass points here. If you can see I've selected all the masses. I'm not gonna plot it, just save it. Okay, let's wait. Okay, well, that was fast. It's saved here. So from here all the way down there, for every single mass, you have a displacement here. So right now, see, this is 140 cyclic frequency. Now, now that we have the data here, I'm gonna say report XY. Make sure I've selected everything. Yeah, so everything is selected. Say OK. It's gonna be saved into abacus.rpt file. Now go ahead, open the temp folder, abacus.rpt. Right click, edit with any text editing software. Now, yeah, here you have displacement, sorry, position versus displacement at the given time 1 second. So go ahead and just select from here to the end and paste it into an Excel file. Control, click that and import the text as different units. Yeah, so make sure you select them as different units. So from here you have 199. In fact, you have 200 points, right? So I'm gonna say 0 to 1, 2, 3, 4, like that. You gotta go up to 199 because you start off with 0 for 200 masses, you gotta end up with 199. So how I'm gonna do that is say this will be my position 0. I'm gonna select fill series column up to 199. Okay, alright, I have all of that here. Now what I'm gonna do is I need the transpose of all of these elements. So I'm just gonna go ahead and um, select these up to the 200th mass. So select all of these equal to transpose of, it needs an array. So from here, oops, oh, yeah, up to the end, you've selected all that. Now don't forget to close it with a bracket and hit Control Shift and Enter. So what you have is, alright, here you're gonna have position versus amplitude or displacement. Now, the next thing I'm going to do is I'm going to have the sine reversal. What I'm doing essentially here is okay, let me first plot this down so you can see what we are dealing with. Whoa, ho, ho, what is this? Yeah, okay. So this is not something I expected, but anyway. This doesn't look like a very good sine wave, but anyway, in the beginning at least, it's a good sine wave. I'm gonna have sine reversal equal to this divided by this, and I'm gonna double click there. So why am I doing this? This is because I want to see where along this displacement there is a sine reversal. See, a sine reversal is where it cuts the x-axis, right? So if I get this point and this point, I will know half the wavelength, right? Yeah, that's what I'm doing. So when I know the sine reversal, select this column and give it a conditional formatting saying any number that is less than 0 must be shaded. So you see, from 214, you have a sine reversal. So that means 14 minus 8, right? Or just 8 minus 2, 6. 6. It takes 6 unit cells to reverse sine. So wavelength will be this 8 minus 2. Sorry, 2 multiplied by that value. Yeah. So wave number will be 1 divided by that value. So QL, as we know it, will be this multiplied by the length, which is 1e minus 3. So yeah, you get the value of QL here. That's how you get QL for a given frequency. And the frequency in this case was, um, I think it was, yeah, 140 cyclic frequency. So yeah, repeat this for different values of omega, and in every case you will end up with a QL, and plot these QL with omega. That will be your dispersion curve. One of the dispersion curves that I did matched with theory.